Hello everyone, I'm Shailen Kasera from ASHRAE Rajasthan chapter. I welcome you on behalf of Delhi chapter of ASHRAE India chapter and ASHRAE Rajasthan chapter. Today we are jointly organizing webinar presentation on low energy chilled beam, and we have eminent speaker Mr. Alan John. We also have Mr. KD Singh, President-elect, Delhi chapter of ASHRAE, and Mr. Manoj Khati from Deccan chapter. Now I would like to start with the ASHRAE Code of Ethics. In this and all other ASHRAE meetings, we will act with honesty, fairness, courtesy, competence, inclusiveness, and respect for others, which exemplify our core values of excellence, commitment, integrity, collaboration, voluntarism, and diversity, and shall avoid all real or perceived conflict of interest. Now I request Mr. KD Singh for welcome address and opening remarks. So over to you, Mr. KD Singh.
Thank you, Shailendra-ji. And good morning and greetings for the day for everybody who is present on this webinar today. The respective chapters, the ASHRAE India chapter, the ASHRAE Rajasthan chapter, the Delhi chapter of ASHRAE, the attendees, and also the attendees from the region at large. So whatever time in the day it is for you, I would say greetings for the day. I think we have a very interesting subject which we are going to cover today, and I think it's going to be a wonderful, a very interesting and eye-opening presentation that is going to happen today. I think most of us as engineers and as practicing consultants or contractors or system integrators and commissioning engineers have heard of chilled beams, but I think something more than that, what is going to be done today is what I would term it as smart chilled beams. Smart chill beams would actually mean a demand control ventilation of the fresh air along with the chilled beams, which already to most of us who understand this are applicable for buildings which have a very efficient envelope, number one, and number two, I think they have proven to save energy, and with using of demand control ventilation with chilled beams, it is said that there would be a further saving of 15 to 20% in terms of the energy consumptions. Also, I think one of post-COVID-19 strategies would be two things. One, it would be to increase the content of fresh air, in the entire in the HVAC system, and number two, conserve energy. And I think the topic that is being covered today, including the radiant cooling, I think one of the other topics that is also likely to be covered today is on radiant cooling. I think it's an excellent strategy post COVID-19, both in terms of energy saving and in terms of in terms of the number of air changes or the fresh air that is required. So I think we look forward, and we have a very, very knowledgeable and wonderful speaker. So with these words, I would welcome you all, and I hope you enjoy the session. Thank you very much. Over to you, Shailendra-ji.
Yeah, I request Mr. Manoj Khati to please introduce our guest. Over to you, Mr. Manoj Khati.
Thank you, Mr. KD Singh. Thank you, Shailendra. Thank you for giving this opportunity. Good morning, friends, members of ASHRAE and ASHRAE. We are organizing this repeat session of this webinar delivered by Mr. Alan Jones. After the first presentation, we received a lot of interest requesting to have a repeat session of this webinar. Our presenter of the day, Mr. Alan Jones, was kind enough to agree for a repeat one. I thank you, Mr. Alan Jones. Friends, Mr. Alan Jones is a mechanical engineer from City University, London. He is also a member of SIPSI. Post his engineering, he joined Hockey Siddeley Aviation Company, and subsequently he moved on to as a design engineer with Carrier Air Conditioning. During his tenure with Carrier Air Conditioning, he worked in markets of UK, Middle East, and Asia. He resigned from Carrier Air Conditioning as Vice President, Carrier Asia. Then in 2008, Mr. Allen founded Barcol Air Company Asia in order to focus on low energy air conditioning system. Mr. Allen, for last 50 years, has been working in this domain, particularly in areas of variable air volume system, chilled beam system, and radiant system. Mr. Allen, now in India, is actively promoting and partnering with H&M Technology Ventures for the promotion of this technology in India. Just a small clarification. The chill beam slide, the chill beam system webinar will take around 1 hour. So we may not be left with more time for radiant system. Maybe subsequently at a later date, we can invite Mr. Allen again for this, for the radiant chill beam, for the radiant system. Now, can I invite Mr. Allen to deliver his webinar, please?
Yes. Okay. Right, I'm trying to bring up my screen. Just give me a moment. Here we go. Okay. So, good morning, everyone, and thank you for logging into our webinar today. As you heard, my name is Alan Jones, and the subject is low energy chilled beam air conditioning systems. My presentation, I would expect, will take about 70 minutes, and I think we've allowed about 10 minutes for a Q&A. You can submit your questions at any time using the chat feature of GoToWebinar, and then I will endeavor to give you my answers at the end of the session. So let's start. So let's start off by reviewing the choices of central air conditioning system in the market today for air conditioning, particularly large buildings. I've listed the available choices here under two categories: what I call legacy systems, and secondly, what I call the latest technology systems. So under the legacy systems, we have, of course, the traditional chill water fan coil system, which I believe you will all be familiar with, and the refrigerant version of that, which is the VRF, or variable refrigerant flow system. These two systems are very similar, except for the type of refrigerant they use, or heat transfer medium, being chilled water for chilled water fan coils and refrigerant gas for VRF. But their functionality, they are almost the same, very similar. The next legacy system is constant air volume system, which is an all-air system with a constant volume of air supplied from an air handling unit to the conditioned space, and then the amount of cooling supplied to the room is varied by varying the supply air temperature, and by changing the chill water flow rate to the air handling unit, or unloading or varying the speed of the compressor for the refrigerant versions. The next system is variable air volume, or VAV, which was developed to reduce the energy consumption of all air systems by supplying constant air temperature and varying the air flow supplied to the conditioned space according to the amount of cooling required. So the idea being to save the fan energy by reducing fan speed and thereby fan power when it's not needed. Now, in the latest technology system category, firstly, there are the chill beam systems, which we will discuss today, and secondly, radiant cooling systems, which, as Mr. Manock mentioned, I don't plan to cover that today, but if you would like me to cover that sometime in the future, I would be happy to do so. So, chill beams were developed in Europe. They were developed as the next advance in low energy systems, and really the next step beyond VAV. They've been very successfully used in Europe after their introduction about 20 years ago, and have now become more and more popular. As a result, they have become a standard HVAC system in much of the world, including now in the US, where they are threatening the dominance of the VAV system for central air conditioning. And they've also become the system of choice for a growing number of users. So what are chill beam systems? So firstly, let me address the name of chill beam in case you are under the impression that it's a concrete beam that can provide air conditioning. Well, that's not quite correct, but maybe the appearance of the units being long and narrow and sometimes being installed below the ceiling was the reason for that name. Their application is mainly for offices and large commercial buildings, but their capabilities are also recognized with other applications, including hospitals, medical facilities, schools, colleges, and laboratories in particular. The differentiator for this system is that it separates the functions of room temperature control from humidity control and ventilation. The operational concept is that using the built-in chilled water heat exchanger in the units, that's used to provide the majority of the room cooling without dehumidification. So the heat exchangers operate dry, unlike the legacy fan coils and VRF systems that operate wet due to condensation. In addition, the chill beam systems incorporate a limited quantity of dehumidified air, which is supplied to the room from a central air handling unit to provide the ventilation and the control of the room humidity. So in this way, the functions of room temperature control and humidity control and ventilation are completely separated. And the benefit of doing that is you get much lower energy use and you improve comfort. There are two basic types of chill beam system, and here I show the schematic for the active type. Active chill beam terminals are installed in the ceiling and incorporate the water-to-air heat exchangers, which provides the majority of the room-sensible cooling. These operate with high-temperature chilled water, typically entering at 16 degrees C and leaving at 19 degrees C. And the reason for using high-temperature water is to ensure there is no condensation on the heat exchanger. In addition, the supply of primary air comes from a central air handling unit, and this is sized to provide the required ventilation and control the space humidity. Now, because the purpose of the air is limited to these two functions, the amount of primary air needed is much less than that required for an all-air system or a VAV system. And typically, the amount of air supplied to a chill beam system could be 30% of the maximum VAV airflow. The primary air also has another role to play in active chill beams, and that is to activate the induction of room air into the beam. And so it induces the room air through the diffuser and through the heat exchanger to mix with the primary air. So the air is drawn through the heat exchanger, and then after mixing with the primary air, that cooled air is discharged into the room through the outlets at the bottom of the chill beams. So in this way, the cooling of the room is carried out completely independently from the control of the room ventilation and humidity control. Now, the second type of chill beam is the passive chill beam. These have the same water-to-air heat exchangers built into the units to provide the room-sensible cooling. They also need a supply of conditioned primary air supplied from the central AHU to provide the ventilation and the control of room humidity. The difference between the passive and the active type is that with the passive type, the primary air is supplied to the room through separate air diffusers, and it's not used to induce room air through the heat exchanger. For the passive chill beams, the air movement through the heat exchanger is driven purely by natural convection. The air in the ceiling void is cooled by the cooling coil, resulting in the air density increasing and the air falling into the room to mix with the room air and cool the room space. Thereafter, the air warms up due to the loads in the room, heat loads in the room, and will rise and return to the ceiling void, completing the natural convection cycle. So to help in the understanding of these systems, it's useful to review the differences between chill beam systems and our traditional legacy systems. So firstly, chill beam systems have a chilled water cooling coil inside the chill beam terminal to cool the room, but no fan, and only use a small quantity of central primary air. So why? Well, chill beam systems are designed to circulate the air through the cooling coil without using built-in fans, based on either using air induction in the active chill beam, or by using natural convection in the passive chill beam. The benefits of this approach is the system uses less energy and is also much quieter than chilled water fan coils or VRF systems or any system using fans to move the air around. A second difference, chill beam cooling coils provide the majority of the room cooling, but do not dehumidify the room air. So why? Well, it is not necessary to dehumidify all the air passing through the cooling coil to control the room humidity. We can fully control the room humidity by supplying the room with a much smaller amount of dehumidified air, and that same air can also provide the ventilation required. So the benefit, with this approach, we only supply the amount of air required to do what is needed, and that is much more efficient and avoids unnecessary dehumidification, which wastes energy. Sorry, I was a bit slow on my slides there, I think. I apologize. So here we're showing the chill beam cooling coils providing the majority of the room cooling, but not the dehumidification. And the benefit of this is by only supplying the amount of air required to do what is needed, it's more efficient and avoids over dehumidification, which wastes energy. So let me move on now. So chill beam terminals use higher chilled water temperature, 16 degrees C, and do not have condensate drain pans, condensate drain pipes, or air filters. So why is that? Well, because it's not necessary for the terminal cooling coils to dehumidify all the air passing through the cooling coil to control the room humidity. Also, by operating with higher chilled water temperature, there is no condensation on the cooling coils. So the benefit, no need for condensate drain pans, which can grow mold and leak, or no need for frequent and intrusive cleaning of cooling coils due to dirt sticking to the wet coil, and no need for air filters when their only purpose is to prevent airborne dust reaching and sticking to the wet coils. And the last difference, why do chill beams beam systems have much smaller primary air handling units and air ducts than all air constant volume or VAV systems. Well, the reason is that with chilled beam systems, the majority of room cooling is done by the chilled beam heat exchanger. The primary air is only used for ventilation and humidity control and provides only a small part, a very small part of the room cooling. The benefit, chilled beam systems only need about 30% of the primary air required by all air and VAV systems. So the AHUs, the air ducting, can all be much smaller and they save a lot of energy. So let's now look closer at the active chilled beam systems. These can provide cooling and heating, and also humidity control and ventilation from the primary air. The units have an air connection for the primary air at the top of the unit, and they have 2 slots at the bottom for the air discharge along each side of the unit. The induced room air enters the unit through the perforated center diffuser, which is directly below the heat exchanger. As you can see from the project photo here, that the ACBs are often arranged in continuous rows. This provides effective air distribution and is also very popular with many architects who like this this type of neat system ceiling appearance. Now, let's look at the operating principle. This slide is showing a section view through the active chill beam. It shows the primary air connector at the top, which connects to the air plenum. This air is typically supplied at around 12 to 16 degrees and has a pressure in the range of 100 to 250 PA or pascals. The plenum distributes the primary air to the multiple air jet nozzles along each side of the unit. As you can see from the enlarged view here, these nozzles along both sides of the unit create air jets which have a low pressure area around the base of the air jet. And these are located above the heat exchanger. So what happens is this low pressure area induces, there we go. This low pressure area induces room air through the induction grill and through the cooling coil before it mixes with the primary air from the nozzles, which is discharged, and then the mixed air is discharged from the outlets along each side of the unit. The amount of primary air is relatively small compared with the amount of induced air and the total amount of air leaving the ACB. And typically, the primary air is only 3 to 5 times, sorry, the total air is 3 to 5 times the amount of primary air. This ratio of the total air versus the primary air is known as the induction ratio. And generally, the higher the induction ratio, the more the cooling performance of the unit, because the more air you have moving through the heat exchanger. Now, looking again at the overall configuration of the active chill beam system, this diagram shows the ACB terminals mounted in the ceiling with the primary air supplied from the air handling unit to create the induction of the room air through the heat exchanger and to provide the room ventilation and humidity control. It also shows the high temperature chill water connections, typically with water at 16 degrees connected to each ACB cooling coil. You can also see that there's an additional chill water supply of 7 degrees C connected to the AHU, to the AHU cooling coil. This lower temperature chilled water is needed for the AHU to ensure the dehumidification of the primary air to control the room humidity. The 2 temperature water supplies are shown here, manifolded together and then connected to the chiller. This is an oversimplification, and I'll explain later the various ways that we create the higher temperature chilled water. To understand the operating conditions of the system, it's better to do this with a psychometric chart. And this chart here shows that the typical operating conditions based on a typical design, room temperature design of 24 degrees C and a room humidity of relative humidity of 55%. Room humidity of 55% or room dew point temperature of 14.5 degrees C is very typical, a very typical design point for chill beam systems, because you want a comfortable humidity level, but you do not want to over dehumidify the space, because this will require more energy input to the system, more cost without providing any more benefit. So based on this room condition, we can derive two important key design points. The first one is the entering chilled water temperature needs to be 1 to 2 degrees higher than the room dew point temperature to eliminate any possibility of condensation on the heat exchanger or elsewhere for that matter. This 1 to 2 degree difference is to allow for the tolerance of the operation of the controls. Condensation will not occur before chilled water temperature drops below the room dew point, but it is safer to allow this safety tolerance because the controls are not 100% accurate. So this chart shows that 16 degrees C is a safe entering water temperature to use with a room design dew point condition of 14.5 degrees C. So it's allowing 1.5 degrees difference as a safety factor or as a controls tolerance, whatever you want to call it. The second design point that we must always consider is that we always need the primary air dew point temperature to be lower than the design room dew point temperature to absorb the room latent load and to control the room humidity. You cannot control the humidity of a room unless you supply the air to that room at a lower humidity. This difference often depends on the number of occupants in a given zone, because people are often the major source of humidity and latent load. So it's quite easy to calculate what dew point temperature you need for your supply air to pick up that latent load and to control the humidity. In this example, we've assumed a primary air dew point temperature of 12 degrees C to provide the amount of dehumidification required. Now, what are the advantages of active chill beam systems? Well, first of all, comfort. As mentioned earlier, the ACB can provide excellent comfort levels, and this includes individual control of the temperature of each room by controlling the water flow to the ACB heat exchanger. So each area that has an ACB can have individual temperature control. We get precise ventilation control due to constant ventilation airflow from the primary air handling unit. We have precise room humidity control by controlling the humidity of the supply air from the air handling unit. Heating is available using either the primary air or by supplying hot water to the 2 or 4 pipe heat exchanger, or it can be by using radiant heating. The noise level is very low. There are no fans to create noise, and typically an NC of less than 30 should be expected. Air distribution is excellent. The air is discharged horizontally under the ceiling, and the Coanda effect ensures that the airstream stays close to the ceiling until the air mixing is complete, and mixed air temperature is the same as the room temperature. So this minimizes any temperature gradients and air drafts in the comfort or the occupied area. Now, a key feature of the system is the energy savings. The exact savings depends on the particulars of the project and the systems being compared with, but on all jobs, the following are the key areas for those savings. The terminals, chill beams have no fans or air filters. Heat exchangers operate dry and stay clean without air blockage. Also, the control of room humidity is independent of room temperature control, so no energy is wasted dehumidifying large amounts of supply air that's only needed for cooling, as does happen with most other systems. The air handling unit, the chill beam system primary airflow is limited to that required for ventilation and humidity control only, and that results in about a 70% reduction in the airflow required versus constant air volume or VAV systems at max flow. Often the air handling units account for 30 to 40% of a system's total energy usage. So if you can reduce the air handling unit airflow by 70%, the fan energy savings alone can be equivalent to 20% saving of the total system energy, compared with like a constant air volume, and 10 to 15 compared with a VAV system. The chillers or the refrigeration, with chill beam systems, 60 to 70% of the room cooling is provided by the high temperature chilled water and the heat exchangers inside the units. So if dedicated chillers are used to produce the high temperature chilled water, there are large energy savings due to the higher chiller COP. The chiller COP gain can result in 30% chiller energy saving for those high temperature chillers. And if the high temperature chilled water is accounting for about 30% of the total cooling used, then it's quite possible to have 10% overall reduction in total chiller kilowatt as a result of using dedicated chillers on the high temperature water circuits. Also, free cooling of high temperature chilled water is a possibility for saving more chiller kilowatt in intermediate season, but that of course depends on the available outside temperature. I believe in India, many places even the winter temperature, it may not be low enough to give you good free cooling. Now, this chart compares the overall energy consumption of the contributing parts of each of a number of competing systems. So here you can see for each system, CAV, fan core, VRF, VAV, etc. What is the relative energy consumption of the different parts of the system: terminal, air handling unit, chiller, etc. And on the far right column, what is the overall impact of those amounts of energy consumption? So you can see here that the constant air volume and fan core systems are categorized as the highest energy consumption systems, and that is due to the high energy use on the terminals or the fan core motors, etc., the air handling unit, and also on the chillers. VAV and VRF are categorized as medium energy consumption due to the energy consumption on the air handling unit and chillers and refrigeration. Active chill beams are categorized as low energy consumption due to the savings on the air handling energy used, and also the possible low energy consumption on the chillers if you use dedicated high temperature chillers. With passive chill beams and radiant cooling systems, These are categorized as the lowest overall energy consumption due to having the lowest energy consumption on the air handling units, and again, low energy consumption on the chillers. Now let's talk about another subject, the reduced ceiling void height. Another big advantage of active chill beam systems. An active chill beam, the ceiling void height need only be about typically 400 millimeters, and that compares with 700 millimeter plus for a fan core or a VAV system. And this is basically due to two things. One, the low height of the terminals. The terminals themselves are less than 240 millimeters generally. And most important, the reduced supply air duct size due to the reduced air volumes. So the air volumes, as the air volumes reduce, and in an active chill beam, the amount of air can be 30% of what is required for constant air volume or a VAV system. Then the ducts get much, much smaller. And that allows for the ceiling to be lifted up. So that, or the ceiling void height can be reduced. So that benefit of the low ceiling void height can be materialized in various ways. This is shown here on this slide. So you look at the second picture there. This is showing that the ceiling height could be raised up from 2.8 meters to 3.1 meters. So an increase of 300 millimeters in the ceiling level. And you would be surprised the effect, the aesthetic effect of raising the ceiling by 300 millimeters. I've seen this on many retrofit projects, which were built as speculative developments with low ceilings, and then you lift up the ceiling by 300 millimeters. It can give a completely different feeling to the space, and can certainly command a completely different rental or sales price. In picture 3 here, it shows another way, and that is to reduce the slab-to-slab height. If it's a new construction, you can reduce maybe from 3.5 meter slab-to-slab to 3.2, and thereby you can facilitate adding more floors to the building in a given height of building. Or picture 4, with active chill beams, they can be installed below the ceiling, exposed without a ceiling. And then the slab-to-slab height can be further reduced to about, say, 2.8 meters. And that is 700 millimeters lower than for a fan core or VAV system. So this benefit of low height can bring a lot of benefit in the appearance or the feeling of the building or the number of floors. The next point is the chill beams are very easy to install. They're normally suspended from the ceiling. They can be integrated into metal panel ceilings, plaster ceilings, or, as we just discussed, mounted exposed. In either case, they should be suspended from the concrete soffit above. They are not suitable to be supported by like suspended ceilings, which are often very flimsy and can hardly support their own weight. So the chill beam should be hung from the ceiling and using either the proprietary wire systems that are available, or most commonly threaded steel rod. Threaded rod is very practical because it's very easy to level the units, to match the units with the level of the ceiling by just unscrewing the leveling nuts, the nuts on the threaded bar. Standard widths of active chill beams are nominal 300 millimeter and 600 wide, which is the same as most metal ceiling systems or any ceiling tiles. So the ACB can be easily matched with most suspended ceiling layouts. Water connections for the heat exchanger, the water-to-air heat exchanger. They can be flare type or screw type, or most commonly in recent years, they are push-on quick lock type connectors. These connectors have built-in O-rings and retaining teeth that grip straight onto the pipe connection. They are very easy to install, and they can also be disconnected if required. And it's also common to use flexible water hoses to connect the ACB units to the water system. This prevents any vibration from the water system being transmitted to the active dual beam, and also it allows for the easy alignment of the active dual beam with the ceiling, and to allow for any relocation of the active dual beams if later renovations are required. Another key advantage is the reduced plant room and ducting space. With the reduced air requirement, if you use 70% less air, you can save a lot of, your handles get much smaller, your ducting gets much smaller, and you can save a lot of plant room space and also ducting space. And of course, it also reduces your ceiling voids, makes the ceiling void much higher, allowing you to have a higher ceiling or a higher slab-to-slab distance. Very little maintenance with active dual beams, because there's no filters to clean, no condensate pipes or drain pipes to leak or to create smells, or even worse, to make a home for bacteria or viruses. No fan motor to repair or to make noise. The cooling coils operate dry, so there's no need for special chemical cleaning as required for systems that operate with condensate on the coils, like the fan coil, chill water fan coil, or the RF system. With the ACB system, the only thing that can happen with the coil is that you may get a little bit of dust accumulated because of electrostatic charges, but a vacuum cleaner will remove any dust, and it's normally found that you really only need to clean the cooling coil every 1 to 2 years. So a quick quick wipe for the diffuser, and a quick vacuum for the cooling coil, and the maintenance is done. Now, all of this leads to excellent life cycle costs. Reduced energy costs, typically 30% energy saving versus constant air volume system, and 20% versus VAV systems. Low maintenance, no fans, filters, or heat exchangers, and the heat exchangers operate dry, so very easy cleaning. Reduced ducting and plant room space, and remodeling flexibility. The ACB terminal can be moved around just like a light fixture. It's a similar size, a similar arrangement. So if you remodel the office, you move partitions, it's very easy to move the system around. Now, the standard arrangements of active dual beams are nominal widths of 300 and 600, and the length is typically in increments of 600 to 300, 3,000, so 3 meters. Excuse me. And that is purposely done to make it a modular system and to fit with modular ceiling panel systems. The diffusers, the center diffusers for the return air is most commonly a perforated type. This is the most popular type, but also linear diffusers are available. And in our experience, perforated is preferred in most parts of the world, but somehow the USA likes to have linear diffusers. They have a different need. So there is a choice, perforated or linear, depend on the architect's preference. Now, units are already fairly low height, but there are also what's known as ultra low height models available. These can be as low as 180 millimeters, which allows for an even more reduction in the height of the ceiling void, even less than the 400 that we discussed earlier. Another version of the active chill beams is what is called a high ventilation type, and this has two additional air discharge slots either side of the active chill beam, which are connected to a secondary air plenum, and that is used to provide additional ventilation air. So these are designed for areas where there may require additional ventilation, such as meeting rooms, conference rooms, etc. They're designed to operate as a normal active chill beam, but when the room occupancy increases and the amount of ventilation air can quickly be increased, keeping the room air fresh and the room well ventilated. The additional ventilation air can be controlled either by opening a supply air damper with a manual switch, or by using a room CO2 sensor for automatic control. The units can provide heating, as I mentioned before, either from the primary air, from the 2 or 4 pipe heat exchanger, or by radiant heating. The induction air panel can be heated by hot water, and that can provide the heat, radiated heat, to the room. Similarly, the same technique can be used for additional radiant cooling. So you cool the center partition, center panel, and that can not only the beam can provide the convective heat transfer, but it can provide the radiant heat transfer to the space. For other types of ACB include four-way air discharge. These are typically used for smaller rooms, so they can improve air distribution on smaller rooms. But they're not normally practical in large offices or open space areas, because in that situation, two-way continuous air discharge normally provides a more comfortable air distribution with less airstream impingement, and therefore unwanted turbulence. Horizontal type active chill beams are also available for installation in a drop bulkhead, which is a typical arrangement for like hotel rooms and other applications like that. And even underfloor units are available, where if you don't have if there is no ceiling or there's no ceiling void, then it's possible to put the active chill beam under the floor and discharge the air from the floor. And there are others, many special configurations. This particular picture here is showing a ACB system specially designed for a school, where the Italian architect wanted a special look with the active chill beams completely hidden behind these floating ceiling panels. The panels were incorporated into the design of the ACB, and also fully acoustically aligned to absorb the reflected sound from the room. So the architect's idea was he wanted to use the active chill beam and the ceiling panel to be an acoustic panel to absorb the children's noise from the room. Now let's talk about the second type of chill beam. That's the passive type, and this is showing here a passive chill beam with its skirt, and also with a perforated diffuser, which is often used to match in with a suspended ceiling with metal panels, making the passive chill beams invisible. Now, the operating principle of the passive chill beam is the beams incorporate the same chilled water heat exchanger as the active type, mounted in the metal casing, and then assembled into the sealing void. The system operates by natural convection. The heat exchanger is supplied with chilled water, and when the air in the sealing void touches the cold fins of the heat exchanger, it is cooled, resulting in the air density increasing and the air falling into the room. This cooled air cools the room, creating a natural convection cycle, and with the cool air being warmed by the room air and the room heat loads, this causes the room to rise to the ceiling and again return to the sealing void, completing the natural convection cycle. The overall configuration of the passive chilled beam system is very similar to the active chilled beam, except with the primary air handling unit with the primary air with the passive beam is supplied directly to the room with separate diffusers, and it's not connected with the passive beam terminal itself. Now, system benefits for passive chilled beam. The benefits of passive chilled beams are quite similar to that for the active chilled beams, and in fact, the energy savings are even better because no energy is used to move the air through the heat exchanger and into the room. However, the cooling capacity is less than an active chilled beam for a similar size heat exchanger due to the lower airflow through the cooling coil. With the natural convection creating the air movement, the velocity of the air is slower than if you use a forced convection, which is what you have with an active chilled beam, using the induction to create forced convection. But the amount of cooling available from passive chilled beams is still more than adequate for building internal zones where you have a limited, the loads are mainly people and equipment. And also for perimeter zones, if you have a good performance facade so that the solar loads are not too high. Now, because there is no direct control over the air discharge from the passive chilled beams, it is important to take care where to locate the terminals to avoid air distribution issues or air drafts. Basically, the air is just dropping into the room due to its higher density and mixing with the room air until it reaches buoyancy level, and then the supply air will be the same temperature as the overall air. So the overall air distribution is acceptable, but you need to avoid this arrangement causing discomfort. If it is and it's a normal practice to locate the beams where the downward airflow will not fall onto occupants. So it is common to install the passive chilled beams along the building perimeter, adjacent to the facade, where the downward cool air can immediately absorb the solar and transmission heat loads coming from the facade, from the outside of the building. Or alternatively, the beams can be installed close to internal walls, where people will not be seated, and there will be no problem with this, the cool air dropping from the unit. Now, where you have high ceilings, like 3.5, 4 meters and above, this concern is no longer an issue, because by the time the cool air reaches the occupied height, it is normally fully mixed with the room air. Now, another thing to take into account with passive chilled beams is the return air configuration. To ensure the natural convection cycle, it's important to avoid obstructions to the return air in the sealing void. And the general rule is to leave a free space above the unit equal to half the width of a passive chilled beam. But of course, this necessitates a higher ceiling void height. So with passive chill beams, typically the ceiling void height would be 600 millimeters or thereabouts. Now, this is showing various configurations of passive chill beams, and in particular, the top picture there shows the unit with an air skirt. It's basically a piece of a ducting installed around the bottom of the heat exchanger. This creates like a chimney effect and enhances the airflow, and it can have quite a dramatic impact on the cooling capacity, because cooling capacities can be increased by as much as 30% by having this piece of ducting to enhance the airflow. Also, as I mentioned before, it's quite common to have passive chill beams to be used with perforated diffusers to match with the metal ceiling. So you look up and all you see is a metal perforated ceiling. The passive chill beams are completely hidden. Now let's change gear a little bit, and now let's talk about the chill beam system controls. There are 4 basic types of control I want to talk about. The first being the individual zone temperature controls. That is room thermostats and chilled water control valves that can control the temperature in each zone. The second is the secondary chilled water temperature controls. That is the controls for particularly the high temperature chilled water, and how we can generate high temperature chilled water if we don't want to create it with high temperature chillers. The next one is the primary air handling unit control, to ensure that we have full control over the room humidity and dew point of the air-conditioned space. And the last one is building pressurization and condensation protection controls. So let's start off with individual zone temperature controls. The cooling output of the chill beams, and thereby the room or zone temperature, is controlled by varying the amount of chilled water we supply to the beams using water control valves and room temperature sensors. So no different for what you would do with a fan coil, chilled water fan coil unit. The temperature control zones need to be selected carefully, as in any other system. It should be determined according to the areas of common usage and occupancy, and with common exposure to perimeter heat loads. So we don't want to have one zone which is covering different facades of the building, which have different heat load profiles due to the different solar loads. We want to have each one of those will have its own zone. And also, if you have a different occupancy, different internal loads, you want to arrange the zones to accommodate that, to give the best possible control. Typically, the maximum control zone area for one temperature sensor, we normally base on 50 meters squared as the maximum, to give a good control over a one zone. The water control valves for this type of control can be 2-way or 3-way, depending on the overall piping system, the design requirement. And on-off control valves are acceptable for small control zones like individual rooms, but for larger control zones, say more than 5 chill beams, modulating valves will provide much better control, because they can vary the amount of water flow, not just on-off. Now, moving on to the water temperature control. Now, this is the control of the water that we're supplying to the chill beams and to the air handling unit. So chill beams need a low temperature and a high temperature chilled water supply. As I mentioned before, there are three methods we use to achieve the higher water temperature. One is water mixing circuit. The second is a heat exchanger circuit, and the last one is to use dedicated chillers for the low temperature circuit and the high temperature circuit. So firstly, the using common chillers with a mixing circuit. So as can be seen from the diagram here, the high temperature chilled water, 16 degrees, is created by mixing low temperature chilled water, 7 degrees, with the return water from the ACB circuit, 19 degrees, using a three-way mixing valve and a circulation pump for the ACB circuit. It's a very simple and effective approach. Works very well, but this approach is not always practical for high-rise buildings because this arrangement needs the same operating water pressure in both the chilled beam water circuits and the chilled water circuit, and the chiller circuit, sorry. So you need the same pressure in the chilled beam water circuit and the chiller circuit because those two circuits are interconnected through the mixing valve. Now, this is okay when the operating pressure in the chiller circuit is maybe less than 5 bar, but it is if it's higher than that, it is probably better to adopt a system which can use a lower water temperature in the chilled beam circuit than in the chiller circuit, because otherwise you are going to have to engineer the water side of the chilled beam circuit to handle the pressure of the chiller circuit, which in the case of high-rise buildings and the static head on the chiller circuit, the pressure can be very high. So if we do need to separate the two circuits to have different operating pressures in the chilled beam circuit and in the chiller circuit, the very easy way to do it, and that's with a water-to-water plate heat exchanger. So you have on one side of the heat exchanger, you have the traditional chiller 7 to 12 supplying chilled water to the air handling units, and then you also take that water flow through the braze plate heat exchanger, and the other side of the heat exchanger, you have the chilled beam circuit for the higher water temperature circuit, or higher water temperature. So, and then you control the flow of the 7-degree water through the heat exchanger to achieve 16-degree water supply for the chilled beams or whatever temperature design requires. This allows to choose much lower operating pressure for the chilled beams, say 5 bar or even less, and it's very useful when the high pressure in the chiller circuit can be 20 bar or plus on a high rise due to the static head resulting from the height of the building. Now the third approach to the high temperature water is in fact the best one, and that is to use dedicated chillers. So you have low temperature chillers operating 7 to 12 degrees C, and then you have the high temperature chillers operating at 16 to 19 degrees. Now the reason for this is that this provides a lot of energy saving on the high temperature chillers due to them producing higher temperature chilled water and the chiller COP increasing a lot. So the energy efficiency of the chiller will be much higher, is much higher, producing a higher temperature water. Now let's talk about humidity and condensation controls. And we have three levels of control or protection. First of all, the control in the building humidity, which is basically done with the primary air treatment. The next is by controlling the building internal pressure to minimize any outside air infiltration. And the third is to have condensation detection just in case there is a need for everything doesn't work, and there's a need to have a backup system. So now let's first look at the treatment of the primary air to control the space humidity. And you can see here in the psychometric chart the typical operating conditions. So as explained earlier, there are two key points to take care of. One is to ensure that the room dew point temperature is controlled to be 1 to 2 degrees above the entrance chill water temperature. Then you avoid any possibility of condensation on the chill beam heat exchangers, or for that matter anywhere. This is the number one important things to do on chill beam systems. If you have the room dew point temperature under control, you have no worries at all about condensation. And in fact, for the many projects that I've been involved in for chill beams, actually I've never had a condensation problem, because we always pay a lot of attention to the overall chill beam system, not just the terminals. The whole system has to be designed as one. The second point is to ensure that the humidity of the primary air supplied to the room is lower than that of the room, to absorb the room latent loads and to maintain and control the dew point temperature at the required level. So it sounds obvious, but you'd be surprised. Some people forget to do this. But it is these two critical points for the primary air treatment, and if they're done right, there's no worries at all about condensation. In the example here, the room dew point temperature is controlled to be 14.5 degrees C. Again, that's the 1.5 degree above the chilled water temperature at 16 degrees C, thereby avoiding any risk of condensation. The primary air supply dew point temperature is at 12, which is low enough to absorb the room latent loads and control the room dew point temperature to the required 14.5. Now, building pressurization. So it is advisable to maintain a positive pressure in the building to prevent air infiltration and the loss of control of the humidity. Having a positive pressure will ensure that the air leakage will flow out of the building and not into the building. It's very easy to do, and you can control the exhaust air fans by using speed control, or even you can use exhaust air dampers to ensure there's a small positive pressure in the building. Now, condensation sensors are also available, and they can be installed. They are installed on the chilled water piping for each zone, or let's say for zones where they feel there's a condensation risk. If the sensor detects that the surrounding air is approaching its dew point temperature, it will close the chilled water control valve. Or alternatively, the system can be configured to increase the secondary chilled water temperature. That's the high temperature circuit water in the area affected. If you increase the temperature above the dew point, then you have no problem. Now, what about the standards for active and passive chilled beams? There are two basic standards, one for active chilled beam and one for passive chilled beams, which relate mainly to the testing and rating of the beams themselves, because that is done in a different type of test room than what you might be used to with like a balanced calorimeter for fan core or air handling unit testing. The test rooms for the chilled beams, and in fact also for radiant cooling, radiant sealants, etc., use a thermally isolated room with controlled surface temperatures. So it's really a room within a room, and the testing is done by balancing the heat heat in to the heat out of the test room. It's important to base on these standards to ensure you get what you expected. Or now we have the more recently introduced ASHRAE version of these standards, which is quite similar. That can also be used to ensure the performance complies with a standard. Now, chill beams can also provide very high levels of air conditioned comfort. In order to ensure this, it's important to be able to quantify the required and achieve comfort levels, not only in terms of the room temperature and humidity levels, but also including room air velocities, temperature gradients, and radiant temperatures. So ASHRAE 55 or ISO 77330 provide a very firm basis for these criteria, and the method determine single comfort value using the criteria of PMV, percentage mean vote, or PPD, percentage of people dissatisfied. Also, the performance, the comfort criteria can be tested, and most manufacturers can assist you in understanding how that testing is done, and also arrange laboratory mock-up testing if needed. Now let's come to the economics. Economics always important. These charts show the comparison of the economics of chill beam versus other available systems, both in terms of capital costs and operating costs. You can see that the active chill beam system has a similar first cost to a VAV system, but it has a lower operating cost. In fact, from the fundamentals of the saving on air movement on active chill beams, in theory, the installed cost of an active chill beam system should be lower than a VAV system. But I guess by being fairly new systems, I think contractors may price them more conservatively than the systems they know. So this makes the cost maybe about equal to active chill beams. So we should expect in the future that active chill beams should be a lower cost solution than VAV. The passive chill beam system has the lowest operating cost, but it has the highest first cost due to its lower cooling capacity than the active chill beam. Now, it's also worthwhile to do an overall comparison of these systems. And here you can see a comparison of the VAV and an active chill beam system by the different aspects. So firstly, on installed cost, you can see that the air handling unit size, plant room space, ducting, ceiling voids are all much smaller for active chill beam systems than for VAV. And that's very obviously due to because we're using much less airflow, and that effect translates into lower installed costs. The operating costs, the fan energy for an active chill beam is much lower due to the using less air, 70% less primary air. Water pumping is a little higher because with an active chill beam system, you have a separate water circuit pumping the water around the chill beams, but that's a very low power system, and will not use a lot of energy. The maintenance is also, much lower. So the total operating, if you look at the total operating costs for the ACB, it has a big positive versus VAV. So you're looking at installed costs similar, but should be a net advantage in the future, and you've got operating costs which are much lower. Now, in terms of comfort, ACP system scores higher on thermal comfort, humidity control, air movement,